Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today we're going to be doing Unit 10, Lesson number 11, known as the Remainder Theorem. The Remainder Theorem is one of the most famous theorems in all of rational algebra. And it's an interesting little theorem. It kind of takes you by surprise. And we're going to take a look at it and develop it in exercise number 1. One thing that would be helpful is making sure that you have your graphing calculator out. Not so much because we're going to be graphing things, but we're going to be evaluating polynomials, and that graphing calculator is going to make it very easy to do that. So make sure to have that out. I'll be giving you a little bit of instruction on it. So let's dive right into it. In exercise 1, it says consider each of the following scenarios where we have p of x divided by x minus a. In each case, simplify the division using a polynomial long division, then evaluate p of a. All right, so in other words, let's take a look at this first thing. I want to simplify this division. I'm going to write it in quotient remainder form. And then I'm going to evaluate not p of negative 2, but p of 2, okay? The way I want you to think about it is if we looked at this denominator and we figured out where it would make it equal to 0, all right, that's what we're going to be evaluating in here. Okay, let me just delete that really quick and maybe switch over to blue. All right, let's do the polynomial long division. All right, let's write this in quotient remainder form. All right, let's divide by x minus 2. All right, so from the last lesson, I put an x there, match it up. I have an x squared minus 2x. Again, I have to subtract here. I'm going to change it to addition and add, and that's going to give me a negative 6x plus 18. Now I have to match up that negative 6x, so I'll put a negative 6 there. That'll give me a negative 6x plus 12. Again, if it makes it easier for you, change and add, and that will give me a remainder of 6. So all of this will be x minus 6 plus lots of 6's here, 6 divided by x minus 2. All right, so we have a remainder of 6. All right. Now what I'm going to do is I'm going to take that polynomial, which is in the numerator, and I'm going to evaluate it at x equals 2. All right, this is where I think that the graphing calculator is very helpful. So just for a moment, let's bring out the TI-84 Plus. All right, and I'd like to review with you how to use the store command on the TI-84 Plus to quickly and effectively evaluate an algebraic expression for a particular value of x. So I want to evaluate this quadratic when x is 2. So what I'm going to do is I'm going to type in 2. Then I'm going to hit the store button, which is right down here. And I'm going to hit that store button. It's going to put a little arrow there on the screen. And now I'm going to type in x. And I hit enter. One of the weird things is then the calculator says 2. And all it's really telling me is that, yeah, I stored 2 in x. Now what I'm going to do is I'm going to type out that quadratic expression. So I'm going to type out x squared minus 8x plus 18. All right, typed it all out, and now I'm going to hit enter. And that 6 that's sitting there is exactly that polynomial evaluated when x was equal to 2. So the numerator, when we evaluated at 2, is equal to 6. Big deal. Whatever, right? Let's do another one. How about this? How about you pause the video now and do the polynomial long division on that one? Okay, pause the video now. Okay, let's go through it. I've got x squared minus 2x minus 25. And I'm going to divide that by x minus 7. I'll have an x here. That'll give me an x squared minus 7x. Again, change, negate everything and add. Makes it easier. Then I'll have 5x minus 25 plus 5. That'll give me 5x minus 35 and change and add, and I'll get a remainder of 10. All right, so all of this would be x plus 5 plus 10 divided by x minus 7. So the remainder is 10. All right, what I'd like you to do really quickly is now come over here and evaluate p of 7. Okay, so again, think about the value of x that makes that denominator equal to 0. Evaluate p of 7. Do that now. All right, well, whether you use store or some other mechanism, it's not too bad, and we get 10. Now, what's going on here? Something seems a little strange. Do you see anything panning out yet that seems a little bit odd? Think about this for a moment. So far, when we evaluate the numerator for that critical value of that denominator, the value of the denominator that makes it equal to 0, we keep getting the remainders. That's kind of cool. All right, well, let's see if that keeps going. Let's do a couple that are a bit different. Pause the video now and think about this. All right, I'm going to clear out the text. Let's take a look at letter C. All right, no big deal. There's a little bit of a typo here. It may not be a typo on your worksheet. Hopefully it's not. This should say p of negative 3. Now, let's take a look. Let's do 2x squared plus 11x plus 11. All right, I'm going to divide by x plus 3. So I'll have a 2x here, and then I'll be a 2x squared plus 6x. I think I can just do the subtraction here. 2x squared minus 2x squared, 11x minus 6x is 5x plus 11. I have to have plus 5. Then that'll be 5x plus 15. Watch myself subtract. 11 minus 15 is negative 4. Now, I want you to understand, I'm now going to evaluate p of negative 3, because again, I want to look at this as x minus negative 3, right? It's always x minus a. Another way to think about it is that we are going to evaluate the numerator at the zero of the denominator, the value of x that makes that 0. Pause the video now and evaluate p of negative 3. And oh my goodness, look at that. It's negative 4. Wow. All right, let's take a look at it one more time. In letter D, why don't you do the whole problem, okay? Okay, let's go through it. And our pattern continues to work just fine. We're discovering the remainder theorem. But let's go through it. Do the division by x plus 4. I have to have a 3x there. It gives me a 3x squared plus 12x. When I subtract, those two would cancel. Here I'd get a negative 5x minus 20. Therefore, I'd have a negative 5 here, negative 5x minus 20. Oh. Change those, I get a remainder of 0. And when I evaluate p of negative 4, I get a remainder of 0. Now this one's a very, very, very special case, okay? Because keep in mind, what we just found was we just really found the fact that this thing has to be x plus 4 times 3x minus 5. And we had a remainder of 0, right? There it is. That may be the most important case of all, right? If we know that that polynomial ends up having a value of 0 at x equals negative 4, then x plus 4 must divide into it nicely. It's got to be a factor of it, all right? Whenever the remainder is 0, then the quantity that's dividing into it has to be a factor of that polynomial. But now I think we can summarize the remainder theorem. First, though, pause the video and think about this slide. Okay, let's summarize the remainder theorem. It's really quite cool. The remainder theorem. When the polynomial p of x is divided by the linear factor x minus a. Now, again, notice it's a very simple linear factor, x minus a, not 2x minus a, not 5x minus a, not x squared minus 2x. Then the remainder will always be p of a. In other words, p of x divided by x minus a is equal to some other polynomial, plus the polynomial at a divided by x minus a. All right? Really, really, really critical, the remainder theorem. And let's apply it. All right, this is a very, very simple application. This would be one of those things where it's just, do you understand the remainder theorem? It says if the ratio x squared minus 11x plus 22 divided by x minus 9 was placed in the form q of x equals r, q of x plus r divided by x minus 9, where q of x is a linear function, then which of the following would be the value of r? Now, one way of doing this is just going through the polynomial long division. So one way of doing this is just using what we did in the last lesson, i.e., you just do this, and do this, and we'll do this, x squared minus 9x, maybe change it, add negative 2x plus 22, then I'd have negative 2, and I'd get negative 2x plus 18, and maybe I'd subtract, and I'd get 4, right? So there it would be, it'd be choice 4. But what the remainder theorem says is, I don't even need to work that hard. All I need to do is take this, that polynomial, x squared minus 11x plus 22, and I just need to evaluate it at 9. All right, I'm going to do this kind of longhand so that we have some faith in how it's working. All right, it would be 81 minus 99 plus 22, which would be 103 minus 99, and that would be 4. Right? So it's remarkable that if you evaluate the numerator at the 0 of the denominator, that gives you the remainder upon division. Really remarkable. We're not going to delve deeply into why that is the case. Okay, we'll leave that for your next course in mathematics, pre-calculus, or whatever you want to call it. But it is remarkable that that works. Pause the video now and think about this problem. Okay, let me clear out the text. All right, by definition, now this is a very important problem. By definition, x minus a is a factor of p of x if p of x divided by x minus a is q of x. So in other words, something is a factor of a polynomial if when we divide the polynomial by that factor, we get another polynomial. Hopefully not the same one. All right, this is like saying that 3 is a divisor, don't know how that got down there. 3 is a divisor of 21 because 21 divided by 3 is 7, right? It's not a fraction here, it's a whole number. Same idea here. So by definition, x minus a is a factor of p of x if p of x divided by x minus a is something nice again, another polynomial. What must be true of the remainder, i.e. p of a, for x minus a to be a factor of p of x? Explain. So what's the remainder gotta be if x minus a is a factor of p of x? Well, let's take a look. I mean, we just had the remainder theorem that said, wait a second, p of x divided by x minus a isn't just q of x, it's q of x plus the remainder divided by x minus a. But we're saying that if x minus a is a factor, this is true. Well, then r must be equal to 0. the remainder must be equal to 0, and this is very important, thus P of A must be equal to 0. And this gives us a wonderful way of knowing whether a simple factor like x minus a, or a simple expression like x minus a, is a factor of a more complicated polynomial. If the polynomial is equal to 0 at the 0 of that factor, well, then that expression is a factor of the polynomial. Sorry, not saying that well. Let's jump into it and see how this can be used. Pause the video now, write down anything you need to, and then we'll take a look at how to use this. And maybe I won't be so confusing. All right, exercise 4. Determine if each of the following are factors of the listed polynomials by evaluating the polynomials. In other words, without trying to factor at all, is x minus 3 a factor of this polynomial? Well, it's this simple. It's going to be a factor if p of 3 is equal to 0. All right? And let me do this the long way. By hand, p of 3 squared minus 11 times 3 plus 24. Well, let's see, that's going to be 9 minus 33 plus 24, and that's negative 24 plus 24, and that's equal to 0. So yes, it is. X minus 3 is a factor of that polynomial. How about x plus 5? Is that a factor of this polynomial? Well, for that, what we're going to want to do is not evaluate p of 5, but p of negative 5. Okay? And again, let's kind of do this the long way. And then we'll have you do the last two on your own, and we'll take a look. Right? So, that'll be 2 times 25 minus 45 minus 2 gives us 50 minus 45 minus 2, and that's equal to 3. 3 doesn't equal to 0, so no. All right, the only way x plus 5 would be a factor of that polynomial is if p of negative 5 was 0. So why don't you try a couple that involve cubics? Use your calculator to evaluate the polynomials. That's absolutely fine. Okay, well, let's go through them. That's a little bit weird that letter D is over here and letter C is over there, but hey, why not? So is x plus 1 a factor of this? Well, if it's a factor, then p of negative 1 should be equal to 0. And in fact, if we evaluate p of negative 1, we do find it's equal to 0. And therefore, yes, x plus 1 is a factor. In this case, is x minus 5 a factor of this cubic? Well, if it is, then p of 5 would have to be equal to 0. And if we evaluate that, we find that p of 5 is equal to negative 5. So no, it's not a factor. All right. And we kind of already had a sense for this a few, well, maybe in the last unit. We looked at graphically factoring something when we were working with polynomials. And we knew the zeros, and we used those to kind of backtrack the factors. And it's really the same way here. We're testing to see if something is a zero. And by knowing whether or not it's a zero of the polynomial, we can know whether some other thing is a factor, right? Okay, pause the video now and write down anything you need to. Okay, I'm going to clear out the text, and then let's do one last problem. All right, exercise number 5. For what value of k will x minus 4 be a factor of x squared plus kx minus 52? Show how you arrived at your answer. All right, pause the video now and think about how you might be able to solve this problem. All right, well, let's go through it. The plain fact is for x minus 4 to be a factor, x equals 4 must solve the following equation. X squared plus kx minus 52 equals 0. X equals 4 must solve this. It must be a 0 of that. All right? Well, if it's going to solve it, then I can substitute it in. I can put a 4 in here, and I can put a 4 in here. And the beautiful thing is that the only thing left is the variable k, or what I'm trying to solve for. So I have 16 plus 4k minus 52 is equal to 0, which would give me 4k minus 36 is equal to 0. 4k is equal to 36, and k is equal to 9. That's the only value of k that will make x minus 4 a factor. What's really kind of cool is you could then go back here and you could say, oh, well, there I have it. I wonder how it actually factors. And the cool thing is it would factor like this. All right, and that, right, negative 4 times 13, a little bit maybe trickier, gives me negative 52. But yeah, as long as there's a 9 there, x minus 4 will be a factor. But the key to doing that problem easily is knowing that x equals 4 would have to be a 0. Okay, pause the video now, and then we'll wrap up the lesson. All right, let's do it. So today we saw one of the most remarkable theorems in rational algebra, what was known as the Remainder Theorem. And the Remainder Theorem, it's kind of hard to state without writing stuff down, basically says if we take a polynomial and we divide it by a simple linear factor, then the remainder that we get can be determined by evaluating the polynomial at the 0 of that factor, or at the 0 of that divisor. See, I told you it wasn't going to work well. One of the nice consequences of that is that we can easily know whether or not a particular binomial is a factor of a particular polynomial by evaluating the polynomial at the 0 that binomial quantity gives us. Not easy to do without writing stuff down. All right. Well, thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.